Okay, section 2.2, we're going to be talking about power functions. And the definition of a power function is here before us. So it's any function that can be written in this form, f of x equals k times x to the a. K and a are both non-zero constants, so we can't have a zero power. We can't have a zero out in front. If we had a zero out in front, that would wipe the whole thing out anyway, so there wouldn't even be a function. It would just be the zero function. So that's why k can't be zero. But ultimately, if we can have something in that form, it's called a power function. Okay? The constant a is the power. We call the k, or the constant a is the power. The k constant is the constant of variation, or we call it the constant of proportion. Okay? And then we're going to deal with some words here in a few minutes, how to actually say, okay, in English, how to say that in terms of proportions and varies. So we say that f of x varies as the ath power of x, okay, or that f is proportional to the ath power of x. Alright, so we're going to talk a little bit more about the vocabulary here in just a minute. But ultimately, a couple key issues here is that this k can be any non-zero number. It could be a whole number, it could be a positive, negative, fraction, decimal, etc. Same thing with a. The power can be any power except for 0. So I could have a fraction power, I could have a negative power, could have a positive power, etc. So all the polynomials that we dealt with, all the quadratic equations in the last section that we dealt with, those were all, if individually, were considered power functions because they were of the form, if I had something like 3x squared, okay, that would fit this format. Okay, the k we would find as 3, the power would be 2, so that would qualify as a power function. True? But on the other hand, if I had 1/2 x to the negative 5, okay, that would also qualify as a power function as well. We have two non-zero k and a values, so that would qualify as a power function too. Fair enough? Okay. So, first thing I want you to look for, though, I should say, is the on page 188. I'll show you that real quick. We have a few examples of some power functions that we use in real life situations. Okay, there's 4 formulas here from math and science. Okay, the circumference formula, area of a circle, force of gravity, and Boyle's law. Those two last ones from science, of course. Okay, these are qualify as power functions. Okay, because as you can see, the variable that we have is r in this case. The constant out in front is the 2 pi, and the power on r is 1. Okay, so ultimately it's linear, if you will. Okay, this one, pi would be the constant of variation, 2 would be the power. This particular formula we consider quadratic, because it's got degree 2, if you will. In this particular situation, we have f and then k over d squared. And so in this case, the k is the constant of variation, and then the power is negative 2. Now, let's talk about that power being negative 2 for a second, because when we have that situation where we have k over d squared, remember having something on the bottom of a fraction, okay, it would be the same as having the fraction, okay, gone, and just have d back up on top, but with a negative power. And one of our rules for exponents is that if we have a negative power, okay, we put it on the bottom and make it positive. Or if it were negative on the bottom, we'd put it on the top and make it positive. And we can go back and forth between any of those versions we choose. But if we write it as a power function, okay, this is not the format of a power function, but this is. Okay, so k would be the constant of variation, negative 2 would be the power. Same thing with that other Boyle's law one, we had k over p. So instead of k over p, we'd write that as k p to the negative 1. And so again, constant of variation would be k, and then the power would be negative 1 in this case. Okay. Now, here's where I mentioned a few minutes ago that we're going to talk about the words. How do we say this in English in terms of varies? We're going to use this idea of varying. Okay. So what we would say in this situation with c equals 2 pi r, when we have a constant of variation of 2 pi, okay, we would say that the circumference of the circle varies directly as its radius. Okay. So any situation where we have the constant times the variable, okay, that's going to be always varies directly. Fair enough? Now, notice in this case I have pi times, again, times r squared. So this one also varies directly. So when we say that, we're going to say the area, okay, and we don't really need to worry about what it's even for, but ultimately Okay, we can say it varies directly as the square of the radius, or we can say it's directly proportional to. Okay, these two things are the same. And when we say varies directly or directly proportional to, okay, those are the same. So these two, they are essentially the same. All right. And notice this time though it's not directly proportional to the radius, it's proportional to the what of the radius. We got to have the square of the radius because it's not just r, it's r squared. Fair enough? Okay. All right, and then in the other ones, here's where we have a different word here that we're going to use. Okay, and if I can get it to not glare, that would be nice. So the force of gravity acting on an object is inversely proportional to, okay, the square of the distance. Okay, so the big key difference is here the variable is on the bottom this time instead of on the top with the constant. Okay, so that's where we use this idea of inversely proportional. Okay. All right, and the other way to say that, okay, is in this Boyle's law, one where it says varies inversely. Okay, so these two are the same. The parts that I have underlined, I could use either of those phrases in either of those sentences. Fair enough? So when we say varies directly, that indicates multiplication between the constant and the variable. Okay? If I say inversely, that indicates division between the constant and the variable. Fair enough? So for instance, in your homework assignment, you might have a problem like this one, number 17. It says the area of an equilateral triangle varies directly as the length of its sides. So your job here would be to write the equation for that. Okay, if you say varies directly, okay, you need to be thinking multiplication or division. Multiplication. And again, it varies directly. And as soon as you see varies in any case, okay, I would write down k. Okay, and if it varies directly, you're going to write down k times. And then whatever it varies directly to is going to be what you're going to multiply by. If that said varies inversely, then we'd wrote, instead of k times, we'd wrote k over. And put whatever the other stuff is on the bottom. Fair enough? Okay. So those two vocabulary parts are important because we need to be able to take a sentence like that, okay, and write a proper equation based on whether it's varying directly or varying inversely. Okay. Questions so far? Okay, next thing we're going to look at then is a particular power function. In this case, we're going to look at the function f of x equals square root, or fourth root of x. Okay, first thing I'm going to do is, their claim is that this is a power function, and if it is, we should be able to state the power and the constant of variation. Okay, this is a power function because we know from our work in algebra that the fourth root is the same as having a 1/4 power. Okay. And hence we can figure out what the k is, and if there's nothing in front of here, what's our k in this case? 1. And what's our power? Our a, if you will. The power is 1/4. And again, it qualifies as a power function because I can write it in the form k times x to the a. So even though the power is not a whole number this time, okay, positive or negative, okay, we have a situation that is still k times x to the a, and we know that k and a can be anything except for 0. So that qualifies as a power function. And they've asked us to analyze it, so let's take a look at the graph of the fourth root of x. Okay, looks very similar to the square root of x, doesn't it? Which is one of our parent functions. Okay. As we can imagine, it should have a similar shape. It does similar stuff to numbers, right? If we put numbers in there, we're finding a number that we can multiply by itself 4 times. If we were to make an XY chart for this, if we wanted to graph this without our calculator, knowing that 0 is going to be my left endpoint, if you will, because I still can't put negatives under here. Nothing times itself 4 times that's negative would give me a positive, if you will. So if I do 0, I'm going to put it 0 in there. Okay. And if I put 1 in there, I'm still going to get 1. But then what next number might I put in here to get a whole number y coordinate? I don't want to put 2 in here because the fourth root of 2 is not a whole number. Okay. If I do 1 to the fourth, it's 1. If If I do 2 to the 4th, that would be 16. So if I put a 16 in there, then I would get a 2 out for my answer, wouldn't it? Okay. And therefore I'd get 16, 2. That's what they have plotted over here. And if you plot those points, you're going to get, again, a similar shape to what we had with the square root function. Okay. All right. Again, analyzing, remember we can always talk about also domain and range here. If I have an even root, okay, the domain is always going to be 0 to infinity, including 0. Range here also goes from 0 and continues to grow, so it would be 0 to infinity also. It's not odd, even, or neither because there's nothing on the left-hand side. Okay. It doesn't have any extreme values because it's going to continue to grow. It's increasing from 0 to infinity, never decreasing, never constant. Okay, so all those analysis questions we should be able to answer with any function we come across at this point. Okay. All right. Now, we're going to another definition that we're going to look at here today, and that's what we call a monomial function. Okay. And this is just a special power function. Notice it's of the same form. It's k times x to the n. We use n this time here for a different power because k, just like in the power function version, it can be anything. But n here, if it's a monomial, if it qualifies as a monomial, n has to be a positive integer. Okay. So some of the functions we've looked at so far have been monomials and some have not. Okay, the one that we just looked at, x to the quarter, is a quarter an integer? A positive integer, more importantly? No, okay. It's not an integer. It's a rational number. So therefore that would not qualify as a monomial. So in other words, what do the powers have to be like? Powers either have to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, all those numbers are fine. Anything but those, then it's not a monomial. All right. And just to relate this back to something that we already know, okay, when we did something like 4x squared plus 2x plus 3, okay, these functions right here, the 4x squared, the 2x, those are considered monomials. Okay, we don't consider that a monomial because the power here would be 0, right? So we still consider this a constant. Okay, so these two would qualify as a monomials. And when we put those monomials together, we get polynomials. Because in Latin, poly means many. So monomial. If we just had these two, we would call that a binomial. If we have all three of these together, we'd call that a trinomial. And then after trinomial, then we just use polynomial. There's no numbers for 4 terms and so on. Okay. All right. So, a couple things about graphing monomial functions. Okay, we already know what the x cubed function looks like. Okay, so our object here is to draw the 3x cubed function, which we know what that 3 is going to do. It's outside the x, so it's going to be a vertical stretch. Okay. So if we had an xy chart for the cubic function, we could just take all the y coordinates and multiply them by 3 and make a new chart, kind of like what we did yesterday. And we could graph that easily enough. Okay. All right. A couple of parts here, a couple of just definitions, if you will, for the graphs of power functions I want to look at. And then we're going to finish up with a problem that we're going to do together in just a second. But if we have a power function, and again, this is any power function, not just monomials this time. Okay, one of the following 3 things happens when x is less than 0. Okay. So if x is less than 0, okay, f of x is undefined, okay, f is even, f is odd. Now, let's look at the pictures here, what we're talking about. Okay. So when we have a power function, okay, we're going to get quite a few different types of graphs here. Okay, this is the graph when a is less than 0. Okay, and actually, let me put a stipulation on that. This was from the. Oh, we're missing a slide. This is a situation where x is greater than 0. Okay, let me put that on there. Okay, if the power is less than 1, okay, we're going to have a function that has that general shape. Okay, if a is greater than 1. Okay, we're going to have this general shape. If a is equal to 1, it's going to be linear. Okay, and if a is between 0 and 1, so if we have a fraction power, if you will, between 0 and 1, it's going to have that square root shape. Fair enough? Okay. If the x is less than 0, so if we have a base, if you will, that's less than 0, something negative, okay, then that's going to take and just create these flips with the same kind of idea. Okay, if it's less than 0, we're going to have this shape. Okay, greater than 0, we're going to have this shape, and so on. Okay. Do we need to memorize that? No. Okay, because ultimately, whatever function you're given, okay, you have the means to graph it. Okay. You know what the parent functions look like, so this isn't anything you have to memorize. These are just some generalizations about the shapes of those graphs.